Thermodynamics is certainly the most complex part of physics that we'll be studying not only in first semester physics but also in second semester physics. The reason is that the familiar equation, PV equals nRT, is the first equation we've encountered in which there are actually four dynamic variables: pressure, volume, number of moles, and the temperature. With four dynamic variables, this equation is well above the level of the course, and so for that reason, in introductory physics, we will assume that the number of moles is constant, reducing the ideal gas law to pressure, volume, and temperature as the three dynamic variables. Despite this significant simplification, PV equals nRT is still very difficult to deal with for the following reason. If we were to plot pressure versus volume, we would find that any possible curve can be achieved. Even though most students would tell you that if the volume is increasing, the pressure must be decreasing, this isn't true at all. It isn't true because we have a third dynamic variable in the temperature. So in fact, the pressure as a function of volume can be any curve whatsoever. The complexity results in trying to evaluate the components in the first law of thermodynamics. As you'll remember, the first law of thermodynamics says that the internal energy of any system can be changed either by flowing heat, that's method number one, or by performing work. Long ago, when studying systems that were either liquids or solids, where the volume changes would be infinitesimal, no work was possible, and so the attributes that should belong to delta U were mistakenly attributed to Q, which is the heat. Now we understand the distinction between these three, and that is delta U is a change in internal energy, which you can imagine directly as being related to a change in temperature. The first law of thermodynamics says that we can either change the temperature by the flow of energy from one system to another, that's heat, that's method one, or by work. Our goal in studying this system as a physics topic is to understand how we can transform internal energy that virtually all systems have into work. We recognize that work is equal to the integral of force times distance, or when placed in terms of continuum mechanics, we have the integral of pressure over volume. This is why it is so important to us to be able to understand how the pressure varies with volume, but unfortunately the freedom allowed by the first law of thermodynamics says that pressure could do anything when you change the volume. For this reason, in this class, we are going to take four special cases of how the pressure will vary with the volume. Three of these special cases are simply holding one at a time each of the dynamic variables found in the ideal gas law a constant. So the first one is pressure equals a constant, and the second one is volume equals a constant. The third one is temperature equals a constant. And the last one occurs simply because it is so important in nature, and that is that there will be no heat flow allowed, meaning that the change in internal energy is directly visible as work. Now, if we step back and view each of these processes, we can see what they look like on a pressure versus volume graph. Pressure equals a constant will be a horizontal line. Volume equals a constant will be a vertical line. And both temperature equals a constant and Q equals 0 will be sloping lines. The Q equals 0 line, which is also known as adiabatic, follows the most natural tendency of any system, and that is, as the system expands, it would cool, and when it contracts, it would heat. As a result, the adiabatic curve is steeper than the isothermal. And so those four curves are as labeled in green. Because there are now four special cases, each case will have a set of three formulas. The three formulas will involve the work done in changing the volume, the heat transfer, and and the change in internal energy. Our quote-unquote table exists simply as a means of organizing this information so that it can be recalled readily. The form of the table is as follows. Each row in the table is a different kind of process: isobaric, isochoric, isothermal, and adiabatic. The columns in this table are the three entities that exist in the first law of thermodynamics. These are the work, the heat, and the change in internal energy. Although the table will have as its total content 12 independent formulas, students should not endeavor to simply remember all 12 of these formulas, but rather to understand how the table is founded. The first step is to look for the zeros. Each quantity, work, heat, and change in internal energy, has one process that is associated where that quantity is zero. Since work is the integral of pressure times change in volume, the only way to make work zero with finite pressure is to not change the volume. And so for that reason, the zero in the work column is in the isochoric or constant volume. Zero heat is the definition of the adiabatic process. And finally, we must remember that internal energy is related directly to temperature. The only way to not change the internal energy is to not change the temperature. And so for this reason, the change in internal energy equals zero happens during the isothermal process. These last two, the heat and the change in internal energy, are the ones that students most often swap by accidentally confusing heat with temperature. It is internal energy that is related to temperature. Therefore, when the temperature doesn't change, it doesn't mean that the heat flow is zero. When the temperature doesn't change, it means the internal energy doesn't change. And there can be heat flow so long as there is work. The next two formulas that appear in the table actually harken back to the times before it was understood that internal energy was related to temperature change. Back in those days, people attempted to find relationships that would be between heat and temperature change. As a result, the specific heat constants were defined and formulated, and two particular formulas come out for an ideal gas. One of them is for constant volume, which is NCV delta T, that we derived by imagining that a gas is composed of microscopic molecules bouncing off of the walls. And the other one comes from an attempt at holding gas at constant pressure, and again attempting to relate heat to temperature change rather than the most natural thing, which is to delta U. Any time in this table that we ever get 2 out of the 3 columns filled in, we immediately know the third column by applying the first law of thermodynamics. Since delta U equals Q minus W, if we ever have 2 out of the 3 of these, we can immediately calculate the third. We have done so in the constant volume row, and as a result we plug in 0 for the work, NCV delta T for the heat, and we find that the change in internal energy must be NCV delta T. If in the earliest studies of thermodynamics people had understood the concept of internal energy, they would have recognized that there is a unique relationship between change in internal energy and change in temperature. This relationship is the same for every row in this table, and therefore we can copy it from top to bottom. Sometimes, having done this, students are a little bit concerned about the subscript V appearing in so many different rows when only one of these rows is the constant volume process. This is okay. There is only one of these rows in which a formula intended for heat was actually the formula that applied to delta U, and that's the row in which work was 0, which is the constant volume process. We recognize in the bottom row that we have 2 out of 3, and so plugging in 0 for the heat and NCV delta T for the change in internal energy, we're able to find the work as minus NCV delta T. Now there are very few steps necessary to complete our entire table. Each of these steps involves an area under a curve. If we look at the first line where we're dealing with constant pressure, then in that case the line will be horizontal and the area will be a box. The box will have a height of P and a width of V2 minus V1. And so we're now done with the constant pressure row. Finally, in class we performed an integral in the case of isothermal, and that integral gave us a natural logarithm so that the work for an isothermal is nRT, natural log V2 over V1. And finally, plugging in our 2 out of 3, we find the same expression holds for Q. This completes our table of 12 formulas. There are 4 rows: constant pressure, constant volume, constant temperature, and adiabatic, which means zero heat flow. And in each one of these rows, we have an explicit relationship for how to find the work, heat, or change in internal energy. Those are the ingredients of the first law of thermodynamics. And it looks like we're almost ready to analyze everything for a heat engine. There are only 2 more things to add. The first is that the constants C sub V and C sub P appear throughout the table, and it's necessary for us to remember where these constants came from. They came as follows: monatomic, diatomic, and polyatomic gases will have different values for the C sub V and C sub P. This is easy to understand. If we look back at the delta U formula, the delta U formula, no matter what the process is NCV delta T. We recognize that depending upon what kind of gas we have, the number of ways you can hide energy internally varies. Monatomic gases can only have the energy as translational kinetic energy. Diatomic gases can have 3 forms of translational kinetic energy, X, Y, and Z, but only 2 forms of rotational energy. Let's remember for a moment what temperature is. We understand temperature to be a relation that is directly proportional to the average translational kinetic energy. Since, for some gases, like diatomic, translational kinetic energy isn't the only way it holds internal energy, the relationship between a temperature change and an internal energy change is going to involve a different constant. As a result, we found the following table. For monatomic gases, we derived 3/2 the ideal gas constant for C sub V. Diatomic, where we gave it 5 degrees of freedom, is 5/2 the ideal gas constant, and polyatomic, we said, was 7/2 the ideal gas constant. Based upon an analysis of the constant pressure process, we find that C sub P is always bigger than C sub V, and it is larger by 1 R, meaning that we get 5/2, 7/2, and 9/2 R as the values for C sub P for each of these gases. Lastly, the factor gamma is defined to be Cp over Cv. Gamma will always be greater than 1. And for these 3 gases, we get 5/3, 7/5, and 9/7. You may ask for a moment, what's so important about gamma? It doesn't seem to appear anywhere in our equations for W, Q, or delta U. The importance is as follows. If we begin with the ideal gas law, where PV equals nRT, we can solve for all of the things that are constant in this relationship, yielding that pressure volume over temperature equals nR. Since in this class we've agreed that we will not allow the number of moles to change in any of our discussions, PV over T is the same at all points along any process. Therefore, P1 V1 over T1 equals P2 V2 over T2. In the case of constant pressure, the P's in this relationship would cancel. Constant volume, the V's would cancel, and similarly constant temperature, the T's would cancel. These will lead us to relationships that tell us the PVT connection between endpoints along any of the processes, constant P, constant V, and constant T. The results we get are as follows. V1 over T1 equals V2 over T2 for constant pressure. P1 over T1 is P2 over T2 for constant volume. And finally, P1 V1 equals P2 V2 for constant temperature. Unfortunately, the adiabatic process is somewhat more complicated because during an adiabatic process, the pressure, the volume, and the temperature all change. And so, simple relationships such as the ones we just got do not hold. This is where gamma comes in. There are two ways to consider how an adiabatic process goes. One is a PV relationship, and the other one is a TV relationship. And these are as follows. P1 V1 to the gamma equals P2 V2 to the gamma, or T1 V1 to the gamma minus 1 power equals T2 V2 to the gamma minus 1 power. These last relationships finish our study of, quote-unquote, the table, which is in fact 3 tables. Let's review very briefly. The table tells us for each of the processes, constant pressure, constant volume, constant temperature, and adiabatic, the 3 ingredients of the first law of thermodynamics: work, heat, and change in internal energy. Because this table relies heavily on the value of CV and CP, we formulate a second table that explains to us how monatomic, diatomic, and polyatomic gases express their CV, CP, and the ratio CP divided by CV of gamma. Finally, although this is quite simple for the constant pressure, constant volume, and constant temperature processes, we evolve PVT relationships that allow us to connect points along the graph. The most important of these, which is where gamma comes in, are the ones for the adiabatic. And that ends our discussion of the ingredients necessary to solve a heat engine, a refrigerator, or a heat pump.